Good morning, everyone. I hope you're all doing well. It's been a long time since we've had a real dynamics lecture, so welcome. I have a question to ask you first. So on Tuesday, I posted lecture videos. Raise your hand if you watched those. Okay, that's great. Okay, that's great. If you have any questions about these videos, I have extra office hours today. I'll be in my office from 12:30, well, from 1 till 3:30. So if you have any questions, pass by or feel free to post questions on ad. Were these kind of understandable, the videos? What were the topics that were discussed in the lecture videos? Yes? Momentum, linear momentum and angular momentum, right? The linear momentum of a particle g is equal to mv. And what is the angular momentum of a particle, say, with respect to a point P? Yes. But I want the angular momentum about the point P. Right. Cross mv or cross g. Remember the moment of the linear momentum. Speaking of moments, if I had a mass of m, particle m, with some force P applied to it, and I want to find the moment of the force P about some point A, say. So the sum of moments about A. The mass is at point P. So what is the sum of moments about A? Or the moment of the force P about A? So I have a particle of mass m at point P. A force P is applied to it. How do I find the moment of force P about point A? This should be quick. You learned about moments in statics, right? Yeah? Okay, so what is the moment of a force about some point? Yes? Not quite. Yes.
Is it R minus RT cross
R minus, what is R? So say I have my origin O. Let's call these position vectors RB and RA. So now what would be the sum of moments about A? Or the moment of the force P about A? Yeah? What would it be? The moment of the force P about point A. And P is applied at point B. Yes?
RP minus RA.
Raise your hand if you agree. Yeah, great. So that's calculating the moment of a force. We should know this. We should be able to calculate very quickly. Okay, what else did we discuss in the online videos? Yeah, what else did we discuss in the online videos from Tuesday's online lecture? Just give me a topic, any topic, anything you remember from the lectures. Conservation of what? Right. We actually talked about two conservations. We previously talked about conservation of energy. And then we talked about conservation of linear momentum. then conservation of angular momentum. And we also talked about conservation along a certain direction or complete. Okay, so let us see when we have each of these conservations. So when is the energy of a system conserved? Under what condition or conditions is the energy of a system conserved? Yes?
No external forces.
Not quite. For example, if you think about kind of the spring pendulum system, if you think of the pendulum, you have the spring force acting on it, gravity acting on it, but still its energy is conserved. You can even think of a simpler projectile motion. The only force acting on it is the weight, and then energy is still conserved. So it's not quite true that energy is conserved when all the external forces are equal to 0. Under what condition is the energy of a system conserved? Actually, what is it? G is the linear momentum, right? So G is constant. That's the linear momentum, so that's not related to energy. When is the energy of a system conserved? Yes. Yes, more precisely, when all the forces doing work on the system are conservative. So the energy Okay, so that's very important. All these notions are very important. We need to know them very quickly. So the energy of a system is conserved when all the forces doing work on the system are conservative. Is the energy of a projectile conserved? Is the energy of a projectile without drag conserved? Think about it. Raise your hand for yes. Raise your hand for no. Raise your hand for yes. Well, okay. Why? What is the energy of a projectile conserved? Discuss it with your friends and then share an answer with me in 1 minute. I'll ask for an answer. Okay, I'll choose someone to answer who didn't answer yet. Maybe you. Why is the energy of a projectile conserved?
Because the weight, like the gravitational force acting on the mass, is conserved.
Right. So your friend is saying, I'll draw the free body diagram of the projectile. The only force acting on it is the weight. The weight is a conservative force, so the energy of the projectile is conserved. Right? Let us consider a more complicated problem. Let me think of a cone. A smooth cone. And I have a particle on it. Okay? Is the energy of this particle conserved? This particle is traveling on a smooth cone. Chat with your neighbors. I'll ask someone for an answer in a couple minutes. Is the energy of this particle conserved? A particle that's moving on a smooth cone. Okay, let us see. Sir, you arrived late to class. Is the energy of the particle conserved? Well, can everyone answer this? That's an easy question. Is the normal force a conservative force? No, it's not. Then no. Well, raise your hand if you agree with your friend. Raise your hand if you disagree. We have a bunch of disagreement. So what's up? What's happening here? If I draw the free body, yes, can you explain what to do?
Ours, because the normal force is perpendicular to the motion, so it doesn't generate any work.
Exactly, right. So if I'll start with the easy steps. I'll draw the free body diagram of the particle. What are the forces acting on the particle? Normal force. What else? Weight. Okay. The weight is a conservative force, right? The normal force is not conservative, non-conservative. But in this problem, like you mentioned, the normal force is workless. Why? Because how do we calculate the work of a force? The work of a force from T1 to T2 is the integral of n dot v dt. N is perpendicular to the cone, v is along the cone, so this is just equal to 0. The normal force is workless. So all the forces doing work on the system, which is just the weight, are conservative, so the energy of the system is conserved. Does that make sense? Does that make sense? If I attach a spring like this to the cone, to the mass, and the spring is fixed at the vertex of the cone, is the energy of the particle conserved? Yes or no? Think about it. So it's the same exact problem, but now I'm attaching a spring to the mass, and the other end of the spring is attached at the vertex of the cone. Is the energy of the particle conserved? Okay, raise your hand for yes. Raise your hand for no. You did not raise your hand. What's your answer? It is. Do you want to help your friend?
I think it's conserved since spring force is conservative, and since it's along it's along the same direction that it's already moving in. And again, we're just adding another force to this free body diagram, so we don't care about the normal force. So the only two acting on it are its weight and then the spring force.
Right. Just be careful. Doesn't matter what the direction of the spring force is, as long as you know. I'm going to add the spring force to the free body diagram now. The spring force is conservative, right? The other forces are still the same, so still the energy of the system is conserved, right? What are the conservative forces that we know in this course that we're going to use? Remember what they are? Weight or any constant force. What else? Yes. The gravitational force between the gravitational force according to Newton between two masses. And then what else? What's the third conservative force? The spring force, exactly. Okay? I need you to review things and to know them very quickly, right? Maybe you've noticed in the first exam, you need to know things very quickly. You need to practice a lot to be able to solve dynamics problems. And the second exam is not going to be easy, right? You still have to solve all the problem sets, solve all the previous exams, and then solve more problems. And you need to know the material very well. So please solve the problems every day. Dynamics is, during a regular semester, we say that it needs 6 hours of outside work per week, outside class per week. In the summer, more, maybe 10 hours of outside work per week need to be dedicated to dynamics, to solving all the problems, and just not reading the solutions, really solving the problems and learning the material well. Agreed? Okay, so this is energy. Any questions? Now, if I add friction, if the cone here is not smooth anymore, if it's a rough cone, is the energy of the particle conserved? No, why not?
Friction is
Exactly. Friction is non-conservative. And is it workless? No. Okay. In what case is the linear momentum of a particle conserved? So we talked about conservation of energy, now linear momentum. In what case is the linear momentum of a particle conserved? So meaning G is constant, linear momentum is conserved. Under what condition is linear momentum of a particle conserved? Meaning G is constant.
no external forces.
Right, exactly. Right, this means that G dot is equal to 0. We already know from the balance of linear momentum that G dot is equal to F. That's F equals ma. So for G dot to be 0, F needs to be equal to 0. Okay? We also know the balance of angular momentum theorem. The sum of moments about O is equal to the h dot O, the rate of change of angular momentum about O. So this is the balance of angular momentum for a particle. The balance of angular momentum for a particle. Is this independent from the balance of linear momentum? This equation, is it an independent law from the balance of linear momentum from F equals ma, or is it derivable from F equals ma? Derivable, right? So it's not independent from F equals ma for a particle. But for a rigid body, for example, it's going to be an independent equation. So in what case is the angular momentum HO constant conserved? What is 0? Not G. In what case is HO conserved? Come on, come on.
M equals 0, H dot is 0.
Right, right. MO is equal to 0, exactly. If the sum of moments about O is 0, then the energy of the then the angular momentum about O is conserved. Can someone give me an example of a problem where the angular momentum about the origin is conserved? Maybe from the exercise problem sets or from the lecture examples. An example where the angular momentum of a system is conserved. Come on, come on. Okay, I'm starting to feel like that we need to have a quiz about this on Tuesday, an individual quiz, shall we? Tell me. If I don't get quick answers, maybe we'll do a quiz to force you to review. An example where the sum of moments about O is 0. From lecture, you can open the problem sets right now and see. Was there a problem where the angular momentum about O was conserved? What is it? There was actually a class of problems where the angular momentum about the origin is conserved, or some fixed point that we'll call the origin is conserved. I'll give you the acronym of the class of problems. What does CFP stand for? Exactly, central force problem. So for example, when you have, say you have a planet orbiting the Earth or a planet orbiting the Sun, the only force between the two bodies, if I take my Sun to be fixed, the only force between the two bodies, or the only force acting on the satellite or the planet, is the gravitational force. And what is the moment of this force about point O? Zero. Why? Right, because the position vector from this to the force R crossed with the force is 0 because the two vectors are perpendicular, right? So that's a central force problem. The angular momentum of the satellite or the planet is conserved. Another problem you had in the problem sets was this problem, basically the spring pendulum, but in the horizontal plane, so there's no gravity. The gravity is perpendicular to the plane. So the only force acting on the mass is the spring force. And what is the moment of the spring force about O? 0. So MO is 0. The angular momentum of the particle is conserved. Does that make sense? Okay, great. So you talked about, or we talked about all of these. The balance laws, remember, F is equal to G dot, the balance of linear momentum. We can integrate this with respect to time. What do we call this equation? Yeah, linear impulse, linear momentum equation. Okay, on this side we have the linear impulse. The linear impulse of a force is the integral of f dt. Is the linear impulse of a force a vector or a scalar? Is the linear impulse of a force a vector or a scalar? Oops. Raise your hand for a vector. Raise your hand for scalar. Discuss. We need an agreement. Okay, raise your hand if you think the linear impulse is a vector. Okay, great. Scalar? Good. Yeah, it's a vector. The integral of f dt, we're summing, the integral is just a continuous sum. So we're summing vectors, the result is a vector. Also, the linear impulse is equal to the linear momentum, or the change in linear momentum, which is also a vector. So So it needs to be a vector, right? We cannot equate vectors and scalars. Okay. You also had the angular impulse, angular momentum equation. The angular impulse, angular momentum equation. Okay. What else did we talk about? There was one big topic, the longest video of all. What is it? Collisions, exactly. Okay. Say I have two colliding particles. I will identify the plane of collision, and I will take my vector t to be tangent to the plane of collision and n to be normal to the plane of collision. Any conservations of maybe energy, linear momentum, or angular momentum of any system, individual particles or combined system of two particles during impact, think about it. I want a list of all the conservations in this problem. Think about it, chat with your neighbors, a list of all the conservations. Do not come to class late anymore. Okay, what conservations do I have? Linear momentum of which system? So your friend is saying we have conservations of linear momentum, correct? Which system though? Along which direction, or is it completely conserved? Any ideas who can help your friend? What conservations do I have? Yes.
Along the tangential axis.
For which system? Is it particle 1, particle 2, or the combined system? The whole system? Right. So if I look at particle 1 and particle 2, if I draw the individual free body diagrams, what are the forces acting on these particles? During collision, what are the forces acting on these particles? We might have the normal force, the weight force in and outside the plane. N1, W1, W1, N1, W2, N2. And your friend is saying in the back we have the impact forces. What is the direction of the impact forces? Are they acting along T, along N, or a combination of these directions? Along N, right? Our assumption is that the impact forces are going to act perpendicular to the plane of collision. From Newton's third law, if particle 1 exerts on particle 2 of impact, the opposite is going to happen on particle 2. Okay, so if I consider the combined system, the sum of the external forces in the plane is 0, right? So for the combined system, okay, for M1 and M2, is the linear momentum of the combined system conserved? Okay, we're having a quiz on that on Tuesday. Get ready. I think you should have watched the videos, and yesterday in the exercise section you also went over these. You had a quiz. You're answering too slow, so quiz on Tuesday. Let's start with today's materials. Today we're looking at systems of rigid bodies, systems of particles. Very exciting. On Tuesday, after our quiz, we'll transition to rigid bodies. And that's what we're going to do until the end of the semester. Rigid bodies are very exciting. So first, systems of particles. This is our setup. We have considered a system of n particles. Okay, for example, particle I has mass mi and position vector Ri with respect to the origin. So consider a system of particles. A typical particle has mass n particles going from 1 to n. A typical particle has mass mi, position vector with respect to the origin Ri. Now what we want to do is, remember, for one particle we define its position vector, its velocity vector, its acceleration vector, its linear momentum, its angular momentum, and then the balance laws. Recall for one particle, we defined the position vector r, the velocity vector v, the acceleration vector a, the linear momentum g, the angular momentum about a point p, and we defined the kinetic energy, scalar. So we defined all these kinematical quantities for one particle. We also defined the balance laws, looked at the balance laws. We had the balance of linear momentum, balance of angular momentum, the work energy theorem, and we had the linear impulse linear momentum equation, the angular impulse angular momentum equation, the integral of these. Okay, we want to find the equivalent of all these kinematical quantities and kinetics equation for a system of particles. And that's going to be good practice for what we're going to do next week, which we're going to repeat this whole process, but for a rigid body. We're going to need to find all these kinematical quantities and laws, balance laws for a rigid body. Any questions about the setup here, our plan? Any questions about our plan? Questions? Okay, cool. We're going to start by defining the center of mass of a rigid, of a system of particles. The center of mass C has position vector RC is equal to the sum of mi Ri over the sum of mi. So for each particle has its individual position vector, and we can define some point C, which we're going to call the center of mass of the system of particles, and that's how C is defined. And we're going to see why we define C this way. The sum from I equals 1 to n. Okay, let's consider an example. Let me consider a dumbbell with mass m, and this side has mass m, this side has mass 4m. Okay, where do you think the location of the center of mass of the dumbbell is going to be? Is it going to be somewhere outside? Is it going to be somewhere on the dumbbell? Yeah, somewhere on the dumbbell closer to 4m. So this is our point C, the position vector of the center of mass. Let us try to find the equation of C exactly. So I'm going to consider a basis. Ex, Ey, and I'm going to consider another basis on the dumbbell. Call it Ex, Ey. And Ex and Ey, the small bases, I want to find RC. Okay, so from the formula, how many particles do I have here in this system? 2 particles. I'm going to consider this rod, the connecting rod between the 2 particles, to be massless. So I have 2 particles really, so RC from the formula is going to be equal to m1 r1 plus m2 r2 over m1 plus m2. So here I call the particles not 1 and 2 but A and B. So MA RA plus MB RB over MA plus MB. Do we agree with this? Okay, great. And then MA is just M. So I'll write MA is just M. Oops. MRA plus 4M RB. Let us see how to write RB and then plus M plus 4M. With me so far? Now in this parenthesis, I still need to add RB. How can I express RB in terms of RA and then maybe other constants? The length of this rod is L. So RB is equal to what? In terms of RA plus other vectors, plus some other vector. Can anyone maybe think about what RB can be written as? Yes? Raise your hand if you agree that I can write RB this way. Yeah. Does that make sense? So RB, just from the definition of summing vectors, I can write it as this vector plus that vector, adding the vectors head to tail. So now, I can simplify this expression to get that RC is RA plus 4 over 5 L EX. So this is the position vector of the center of mass. Did I make any mistakes? But we're going to have MRA plus 4 MRA, so 5 MRA over 5. Okay, so we're going to be left with RA plus 4 over 5 LEX. So then what is the distance between A and C? Between A and the center of mass along the rod? What is this distance equal to? If the whole thing is L, what is this distance equal to? 4 over 5 L. Okay? Does that make sense? Any questions? Okay. So that's the position vector of the center of mass C. We can write the velocity of the center of mass as a derivative of RC. So VC is RC dot, which is can be written as the sum I equals of MI VI over sum of MI. And then AC is VC dot is equal to the sum I equals 1 to N of MI AI over the sum of MI. Okay? So if we go back to our checklist, we define R, V, and A for the system of particles so far. Questions? Next, linear momentum. The linear momentum of a system of particles is equal to the sum of the linear momenta of the constituents. Let me write that. So the linear momentum of the system of particles is the sum of the linear momenta of each individual particle. Can I write the linear momentum of the system in terms of the linear momentum of the center of mass? If we consider the system of particles to be equivalent to one particle, with mass m being the total mass of the system and v being the velocity of the center of mass of the system, which is the sum of mi vi over the sum of mi, then over m, then we can write the linear momentum of the system as basically the total mass times Vc, right? So the sum of mi vi is mvc. So the linear momentum of the system is equivalent to the linear momentum of some equivalent particle whose mass is the total mass of the system and whose velocity is equal to the velocity of the center of mass of the system. Okay? So that's the linear momentum of the system. Sum of mi vi equal to the sum of m vc. M is the total mass. Vc is the velocity of the center of mass. Questions? Okay. So we did G. Now we have to look at the angular momentum of the system. Okay, angular momentum. Let me actually say the angular momentum of the system is also equal to the sum of the angular momenta of the individual constituents. The angular momentum of the system So the angular momentum of the system about point P, for example, is the sum of the angular momentum of each particle about point P. So for particle I, how do I calculate its angular momentum about point P? Yes. Exactly. Okay? It's the same formula we had for one particle, but now the particle is particle I, so I'm going to sub-index everything by I. So then for the system of particles, I can write the angular momentum as the sum I equals 1 to n Ri minus Rp cross mi vi. For example, what would the angular momentum of this system about the center of mass C be equal to? not the kinetic energy of the system of particles, but the sum of the kinetic energy of the kinetic energy of the constituent particles. So then T would be the sum of Ti scalar, which is the sum of half Mi Vi dot Vi. Okay. What I want to show right now is that the kinetic energy of the system is not equal to the kinetic energy of the center of mass. So I want to show that T is different okay. So to do this, I'm going to introduce Vc in this equation. Okay, any questions so far? Questions? Okay. So I'm going to introduce Vc. I'm going to say that that's equal to half Mi Vi minus Vc plus Vc dotted with Vi minus Vc plus Vc. And then I'm going to expand. Consider this to be one term, this to be the other term. So that I'll get the sum half Mi Vi minus Vc dot Vi minus Vc plus 2 times the sum of 1/2 Mi Vi minus Vc dot Vc plus the sum of half Mi Vc dot Vc. In this term, I can take Vc and Vc outside. I'll get half M Vc dot Vc. This term really I cannot simplify as is. This term is going to be equal to, well, that's going to be your quiz. It's a quick 10-minute quiz. What is this term going to be equal to? What does it simplify to? This term. You can do it in pairs. It should take you 5 minutes. Each pair will submit one paper. What does this term simplify to? You can use the extra paper as scratch. Each pair should submit one paper. What is it? Yes, the second term. What is it going to be equal to? Simplify it as much as possible. Yeah. You can work individually or in pairs, whatever you like. There you go. Okay. Here you go. Okay. Not the last term, the middle term. I'm asking the middle
Oh,
term.
no, but like the last of the middle term.
Okay, write it down very carefully and explain why. No, VC is not here.
No, no,
We can't read. We can't read.
Oh no, that's VC. VC. You should know from expanding. You don't need to copy, you can expand these terms. Okay? You have to be very careful and precise. Your ER here should point this direction, not that, this. Opposite to this. Right, this is correct. This is wrong. Your points in the opposite direction. And then theta points outside the base, and theta is opposite. Yeah, that's only when the particle is here, but when the particle is here, ER is opposite.
Oh, sorry, I forgot. Were we doing the entire?
No, the middle one. Middle one. Done? No?
No. Is it in the right direction?
Yeah, almost done. But where's the dot product? Where did it go exactly? What does it mean to multiply two vectors? Where did the dot product go? Where did the dot product go? There was a dot and suddenly it disappeared.
Oh, by adjusting different
You're
dots.
doing magic, not dynamics. Yeah. Add the dot and that fixes everything.
Okay.
Very close. What are you doing?
I have it expanded, and now I
Yeah.
figure out what's next.
Okay. Figure it out quickly then. Yeah, 5 more minutes. What does V sub nothing mean? Be careful with your vector signs with your dot product. Then what? That's not the most simplified version. That's, you can simplify further. So we're just looking at the middle term. The last sentence? Yeah.
Move this out.
I mean, you can, but I think there's a reason why you wanted the 1/2 there.
Well, like for example, you can split this into two, then these are the same
It's a very simple calculation. It should be very simple calculation. Okay, but that's correct, but it doesn't have to be this complicated.
No, that's embarrassing. We did the same work pretty much.
Yeah, but look how much simpler this one is.
Oh, this is just all the previous steps.
Yeah, Joyce's didn't need to add VC and subtract VC, basically.
Eh?
You didn't need to add and subtract. Oh, wait. Oh, you were just copying here. Oh, I'm sorry, I didn't pay attention. Then it's the same thing. Okay, no, good job. Good job.
I took a snapshot.
Yeah, good job. Okay. Think about the trick we used about removing, if a term does not depend on I, we can take it outside the sum. Think about that trick. And then VC is the sum of MI, VI over the total mass. That's the relationship between the two.
Sum of MIBI, and then minus MVC dot VC. You know this is MVC squared. Yeah. And here that the sum
How
of
did you go
MIBI
from here to here?
is equal to VC
Oh, VC
times M. This
Okay,
is
so
sum
we're
of MI.
replacing VI instead
Yeah.
of VC.
Mm-hmm.
Okay, yeah.
So then why do you still have
And
the
then you
sum?
get MVC squared minus MVC squared, which is just,
VC.
I think that's it.
Okay, then what is this equal to?
Sum of VC over M.
So what did you get? 0? Can I see? Half MI minus VC dot VC half. Okay. Put your equal sign. Why did you multiply? Well, you multiply by 2 is fine. Okay, put the equal sign between the steps, VI, MI, VI, and then you can take this. Yeah, make sure you're specifying what you're taking outside the integral and stuff.
Okay, yeah. I'll do it.
Okay, good job. Questions?
Yeah, I guess, yeah, could I plug in like VC here, but then?
Yeah, we can replace the sum of MI, VI by MVC.
I thought we were going to just heat it up on the stove.
Because you can control the temperature.
Should be simpler, should be simpler. Maybe you can ask your neighbors behind you to help you out. Done?
The system as like a, just like as its own object. And let's say that GC is actually equal to VC.
GC is equal to MVC. That's by definition what GC is. There's no G. There's G of the center of mass. G. Okay. Okay. Couple more minutes. You can ask your friends, your neighbors for help. Maybe you want to help your friend. Hey, do you need any help? Okay, maybe you can help. No, don't let her copy. Help. Or cheat. Okay, 2 more minutes. Done? The answer should be 0. If you didn't get that, then you're not done.
Oh, okay.
Maybe you can ask your neighbors for help.
She was just this.
Okay, time is up. Please hand in your papers. I want one paper per team. Make sure the names of all the team members are on the paper. So one paper per team. Please put them here on the front desk. One paper per team. Put them on the front desk. 5, 4, 3. Okay. So this is it. This is how we do I have all the copies, all the quizzes? This is how we calculate the kinetic energy of the system. Usually it's easiest to calculate the kinetic energy by just summing the kinetic energies of the constituent particles. The sum half MIVI. The sum of half MIVI. Just be careful. We did all this calculation to show that half MIVI, the sum of half MIVI is not half MVC dot VC. We have this additional term here. So we cannot consider that the kinetic energy of the particle or of the system of particles to be equal to the kinetic energy of the particle's total mass m and velocity vc. We cannot do that. Okay? Cool. So where are we so far? We finished our kinematical quantities. For the kinetics, it's easy. We basically just have to sum the balance laws for each individual particle to get the balance law for the system. So to get the balance law for the system, so to obtain the balance law of the system, you sum the individual balance laws for the individual particles. So for example, the balance of linear momentum. For each particle, I have the sum, for each particle, excuse me, I have Fi equals G dot I. Basically, Fi equals Mi AI for each particle. And then for the system, I'll sum the individual balance laws. The sum of fi, I will call this f, and the sum of g dot I, that's what we define to be. So the sum of the linear momenta of the constituents is the linear momentum of the system. So that's the balance of linear momentum for the system. F is the sum of the forces, sum of all external forces acting on system. You know, the internal forces, they will cancel out from Newton's third law. And then G dot is the linear momentum of the system. The rate of change of the linear momentum of the system. G is the sum of mi vi, which is mvc. We just defined G. Any questions? Okay. Balance of angular momentum. Let's look at our expression for HP. It was equal to the sum of Ri minus Rp cross Mi Vi or G. Okay? Questions? I'm going to take the derivative of this. H dot P is equal to the sum of Vi minus Vp cross Mi Vi plus the sum of Ri minus Rp cross Mi Ai. Did I do any mistakes? Did I make any mistakes? Let's consider this last term. I'm gonna call it term cross. Sum of Ri minus Rp cross Mi Ai. What is Mi Ai equal to? From the balance of linear momentum. Right, Fi. From the balance of linear momentum, Fi is equal to Mi Ai. So I can replace this by the sum of Ri minus Rp cross Fi. Does this expression remind anyone of anything? What is it? Exactly, sum of moments, right? So that's the sum of moments acting on each particle. So individually, that's MP on particle I, the sum of moments acting, or the sum of moments about P, or the sum of moments of the forces acting on particle I about P. again, because of the sum, I get MP. The sum of all the forces acting on all the particles about point P. So then our expression becomes H dot P is equal to the sum of VI minus VP cross MI VI plus MP. We usually take this term to the other side to get MP is equal to H dot P plus the sum of VI minus VP cross MI VI. I can even expand this cross product. If I calculate VI cross VI, what do I get? I can expand the cross product. If I calculate VI cross VI, what do I get? VI cross VI, or any vector times cross with itself is what? 0. So I'll get H dot P plus or minus VP. I can take it outside the cross product. MVC. So this is the balance of angular momentum for a system of particles. So the system of particles, we abbreviate that by SOP about any point P. I'll give you a minute to catch up and then let me know if you have any questions. I am expecting a few questions here about the last step, so think about it, questions, and then let me know what you have. What questions you have. Yes.
So from like right outside the box, right, like H dot P is equal to sigma whatever
Mm-hmm.
to into the box, and then can you change the signs with HD, but there's no change in sign.
Oh, there should be, you're right. So there should be a minus sign here. Which gives us a plus sign here. Thank you. Any other questions? Questions? Do we all know how we got from this step to this step? Questions? Okay. So that's the balance of angular momentum about point P, and we can simplify it if we take the balance of angular momentum about C, the center of mass. How does this equation simplify? I'll get MC is equal to what? How does this equation simplify? Is if I'm calculating the balance of angular momentum about the center of mass C instead of some random point P. Yeah, I'll get H dot C plus what? Plus what? If I look at this, what do I get in this term? I'll get VC cross MVC, which is what? 0. So that's MC is equal to H dot C. So very simplified expression about the center of mass. Okay. And then about a fixed point O, or a fixed origin O. I'll get MO is equal to what? H dot O plus what? Plus VO cross MVC. But what is VO if O is a fixed point? If O is a fixed point, then what is its velocity? 0. So that we're just left with MO is equal to H dot. So we have 3 forms of the balance of angular momentum. All of these are equivalent. This is about any point P, moving point, about the center of mass, and about a fixed origin or fixed point O. Okay? Questions? Yes. Yeah. VC cross MVC is the cross product of 2 parallel vectors. Yeah, that's going to be 0. Any other questions? Okay, where are we in our master plan so far? We looked at the balance of linear momentum and balance of angular momentum of the system. And then for the integral forms, they're going to be the same. Same exact expressions for integral forms and conservations. So let me, yeah. Same exact. For SOPs, we have the same forms for the integral equations, the time integral equations, and same concepts for the conservations. Okay, so our last order of business is the work energy theorem for a system of particles. Let me erase here. Oops, go down. Okay. The work energy theorem for a system of particles. Okay. So for each individual particle, we have its own work energy theorem, which is that T2 I. Let me write this maybe that way. The kinetic energy at T2 of I minus the kinetic energy Ti of T1 is equal to the work of the forces Fi from 1 to 2. That's for particle I. And then for all the system, we sum the work energy theorem equation for each particle. So for the whole system, we get the sum of Ti at T2 minus the sum of Ti at T1 is equal to the sum of the work of the forces 1 to 2. Okay? So, and then we already said the sum of the kinetic energies. Let's just erase that. But the sum of the kinetic energies, that's what we define to be the kinetic energy of the system. So that's the kinetic energy T at time T2 minus the kinetic energy T at time T1 is equal to the work of the forces Fi from 1 to 2. Okay, we previously defined Okay. A few questions arise when we're talking about the work energy theorem for a system of particles. First of all, calculating the work of a force. For one particle, we said that the work of the force acting on the particle is equal to the integral of f dot v dt, or the integral of f dot dr. Okay, so that was for one particle where we have a force F acting on a particle with velocity v or with position vector from the origin r. But when we have a system of particles, which position vector should we choose? Which velocity should we choose to calculate the work of the force? From C, not quite. It's going to be, the velocity does not depend on C. The velocity is independent of the origin. So you can look at the velocity or the displacement. Displacement is also, dr is also dependent of the origin. But we have to be careful. It's going to be the velocity or the displacement of the point of application of the force. So for a system of particles, or in general, in this equation, v or dr are the velocity or displacement respectively of the point of application of the force. Okay, v dr are the velocity and displacement of the point of application of the force. So for example, for example, let's consider the dumbbell system. M1, M2, having velocity, say V1. Well, I'm not going to plot the velocities. I'm going to say this is F1 and this is F2. How do I calculate the work of the force F1? The work of F1 is the integral of F1 dotted with the velocity of which point? If I want to calculate the work of the force F1, that's the force F1 dotted with the velocity of which point? R1, exactly, not C. Be careful. Great thing that you did that, that you said that. No, it's not C, it's R1. R1, that is the point of application, right? That is the point of application, sorry. That is the point of application of the force F1. Okay? Similarly, if I want to calculate the work of F2, I'll dot that with the velocity of which point? The velocity of which point? V2, right? The point of the velocity of M2, which is V2, the point of application of F2. Does that make sense? Okay. Later on, when we're working with rigid bodies, the same concept applies. So say I have a plate that is pinned at its end here, fixed end O. What are the forces acting on the plate? No, not, there's the weight. acting at its center of mass, but there is no normal force here. There is, remember your statics, when you have a pin and you remove the pin, what do you have left? Remember you talked about rollers, you talked about pins, right? Didn't you, in statics? So what's the resultant force due to a pin? Not a normal force, some reaction force, right? So some reaction force at the pin O. Okay? What is the work of the reaction force at O? 0. Exactly. Why? Because the work of RO from 1 to 2 is the integral of RO dotted with the velocity of which point? The velocity of which point? Oh, which is its point of application, and VO is 0. So RO is workless. Also, if I want to calculate the work of the weight, I look at the displacement, the vertical displacement of which point? Exactly, the center of mass, that is the point of application of the weight. Different points on this body have different velocities, they have different displacements. To calculate the work of the force applied at a certain point, I have to look at the velocity and displacement of that point. Okay? So that's one note for the work energy theorem. The other note is that the internal forces do not necessarily cancel out. Note. So let's consider this system. Dumbbell. Actually, I don't have to consider a spring. I can consider the simple dumbbell system again. Okay, that's our simplest example of a system of particles. Dumbbell system, this is a rigid rod of length L, mass 0, M1, M2. And I will consider the following free body diagram of the system. Say I take this dumbbell and I just throw it, okay, in the vertical plane, EX and EY. And gravity is pointing downwards. Okay. What are the free? Let us draw the free body diagrams of each mass. We have on M1 we have W1. On M2 we have W2. What else? Any other forces acting on the system? The tension force is right. And this is a two-force member. It's massless and no forces are acting on it in the middle. So the tension force is going to be along the bar. You remember two force members from statics? So I have like the tension force and minus the tension force. Okay. If I want to apply the work energy theorem, well, first, if I want to sum F equals ma for the combined system, will the tension force cancel out? Yes. But if I apply the work energy theorem for the whole system, will the tangent force cancel out? Let us think. So this is our formula. The sum of the kinetic energies, or the kinetic energy of the system, have M1. Actually, let me call these particles A and B, and I'll keep 1 and 2 to refer to T1 and T2. So A, B, B. Okay, have MA VA dot VA at time. Well, the kinetic energy of the system is half MA VA dot VA plus half MB VB dot VB. Right? Okay, and I can say the kinetic energy of the system at time T2 minus the kinetic energy of the system at time T1 is the work of all the forces. So the work of W1 plus the work of W2 plus the work of the tension force acting on A and then plus the work of minus the tension force that's acting on B. Now if I look at these, this is equal to the integral of t dot the velocity of which point? The A, right? And then this one is minus t dotted with the velocity of point B dt. Do these terms cancel out? No, they would only cancel out if what? VA and VB are equal. But VA and VB are not necessarily equal, right? They're only equal if the whole thing is just translating. So we have to be careful